If you look at standard tutorials for building AI systems, they present a sterile, orderly world, much like this perfectly formatted sandbox. The accepted best practice for structured data extraction always dictates the exact same initial step. Engineers are taught to set the model's temperature parameter to 0. The goal is to force the AI to produce low-variance, highly predictable JSON, a lightweight data formatting standard that computers can easily parse. But enterprise data does not exist in a sandbox. Real-world inputs look like this email thread, a chaotic heap of forwarded messages, overlapping headers, disjointed line breaks, and conflicting signature blocks. When you apply a zero-temperature model to this kind of adversarial, unstructured text, the strict constraint forces a highly specific failure mode. By demanding absolute certainty, the system prioritizes aesthetic formatting over actual information gathering. It returns a perfectly parsable payload that is missing the exact details you need. Consider how a zero-temperature model evaluates a partially occluded or ambiguous text field, like a job title buried deep within an email signature. On the zero-temperature path, the model acts with caution. Instead of guessing, it drops the weak signal. The job title vanishes into a void, gliding seamlessly through validation without errors. The database accepts it. The UI displays a blank, and analytics logs a non-entity. This is silent data loss. A pipeline that explicitly crashes generates an error report you can debug. A pipeline that quietly erases partial truths creates records that look entirely legitimate. Your downstream code cannot distinguish between data that does not exist and data the model was simply too timid to extract. Fixing this requires an architectural pivot that directly violates the standard playbook. You have to deliberately turn the extraction temperature up to 1. This alters the model's operational role. At temperature 0, it acts as a cautious intern who only writes down what they are absolutely sure about. At temperature 1, the model becomes a generous stenographer, writing down everything it thinks it heard so you can verify it later. On the temperature 1 path, the JSON payload expands rapidly, capturing multiple imperfect candidate strings for the job title instead of a blank. The trade-off is visible. The system deliberately ingests noise, returning run-on sentences and formatting artifacts mixed with valid data. This establishes the core engineering constraint for this initial stage. The compute layer must optimize strictly for recall. The priority is ensuring weak signals survive ingestion. If an imperfect candidate never enters the system, it can never be verified, enriched, or corrected. Capturing a messy string gives your architecture a baseline to work with. You cannot simply bump high-variance stenographer-generated text directly into a database. You need a rigid orchestration layer to manage the chaos. This diagram shows a workflow built using LangGraph, a code library for orchestrating large language models. It enforces 3 specific sequential nodes: extract, research, and validate. When dealing with high variance, developers are tempted to use conditional routing, branching the workflow into complex paths. But early conditional branching relies on weak proxies. If a proxy evaluates incorrectly, the entire route is wrong, generating infinite edge cases. By forcing a linear pipeline, the system behaves like a predictable, auditable ledger. During a production incident, every trace you examine follows the exact same 3 stages, making the failure legible. When debugging real-world AI failures from logs, strict consistency and a fixed path easily outperform clever dynamic routing. The final node of this linear pipeline is where the generosity ends. This is where traditional deterministic software engineering reasserts control over the AI. The first layer of validation applies aggressive structural sanitization to the incoming JSON payload to catch specific oddities generated by the language model. This diagram demonstrates that process. The model will frequently output explicit string literals, spelling out words like null, NA, or unknown. The sanitization layer intercepts these text strings and collapses them into programmatic empty values. If those literal strings slip through, downstream systems treat the word unknown as a user-provided value. Sanitizing them out early prevents insidious rendering bugs in the user interface and protects analytics from corruption. The second layer of validation acts as a hallucination bouncer. It applies blunt, domain-specific logic constraints to evaluate field content. Looking at the job title field, we apply exact deterministic rules. If a candidate title is longer than 60 characters or contains sentence boundaries, it hits a rigid line and is instantly rejected. Blunt, programmatic constraints reflecting actual domain boundaries are highly effective. They provide significantly more reliable safety rails than passing the data through complex embedding checks or a secondary AI safety model. The data packet has now completed its journey. It started as an adversarial email input, was captured by a generous high-recall extractor, and survived a strict deterministic validation node. A standard low-temperature extractor is brittle. It shatters or goes silent when the input gets rough. This architecture operates like the suspension system shown here, utilizing high recall combined with robust shock absorbers to maintain momentum over erratic data. The responsibility shifts. The language model operates purely as a compute layer, generating possibilities. It is the system architecture built around it that curates those possibilities and produces the final record. Extraction is not truth. Validation is where truth enters the system. By shifting the burden of truth away from a probabilistic model and onto a deterministic architecture, engineers can stop fighting the inherent nature of the AI. Instead, they can build resilient systems that survive contact with reality.